Okay guys, Bismillah ar-Rahman ar-Rahim. So what we will be doing today, we will see the organ system involved in the metabolic pathways. What are the different organs and how they are integrated in the control of metabolism. Tamam? So this will be our line of action. We'll see some quick review of the metabolic pathways, some organ involved, some metabolic pathways, and then homeostasis. So as you know that metabolism is highly organized mechanism, well organized, well structured mechanism is the metabolism. It is not randomly assigned or randomly designed, and the normal system goes when it is organized, and there is derangement in this organization, it gives us diseases. So for example, there is a normal glucose metabolism, you have anabolic action, you have catabolic pathways, normal level of the blood glucose, and there is a derangement in that normal metabolic pathways. So we come up with hyperglycemia or hypoglycemia. Normal cholesterol metabolism, if we have normal system of the cholesterol metabolism in control, and the body system and the organs they are participating normally, so we have normal cholesterol level. If there is a derangement, then we can come up with the hypercholesterolemia, and then the sequence of the hypercholesterolemia lead to coronary artery disease, atherosclerosis, and hypertension, and so on. So that's why the normal system is very much important. And as a matter of fact, we know that all the metabolic processes, they are governed around the production of energy, and energy is in the form of ATP. Energy is in the form of ATP. So the major role of the metabolism is to capture chemical energy from the foodstuffs in the form of ATP, utilizes energy to give energy. Yes, boss? Yeah, it is with this. Okay, no problem. Utilizes energy to provide you the energy. So this is the normal mechanism, that how the metabolic processes run and how the metabolic processes work. So human generates ATP by the oxidation of carbohydrate, by oxidation of fat, and to some extent by the oxidation of protein as well, or amino acid as well. And this level, the simplest level, is called the homeostasis, energy homeostasis. And the whole story moves around the demand and the supply. So if we have if the balance is there, the people will not be starved or not obese. But when the balance is disturbed, more expenditure, less input will go to starvation, more input and less expenditure will go to obesity, will lead to obesity. So we know that these are the catabolic processes generate energy, and we, if we remember our previous sessions, energy can come from two mechanisms. Number one, the shortest, the quick, by the substrate level phosphorylation. And number two, higher amount, longer process, by the utilization of reducing equivalents, oxidative phosphorylation. Clear? So we have a shortest mechanism and we have a long mechanism. And outcome is the ATP. Outcome is the ATP. So metabolic fuels, protein, carbohydrate, and lipids, and then they give us the energy in the form of calories, ATPs, which give us this in the form of calories, and 1 calorie is denoted as 1 kilocalorie. And if we define it, that what is 1 kilocalorie or 1 calorie, so it is 111 energy required to raise the temperature of 1 kilogram of water for 1 degree Celsius. So this is 1 kilocalorie. So this is how the mechanism goes on, and these are the stuffs. These are the stuff. Breakdown, give you this one with addition to this, and then combination of these smallest molecule will give us the higher structure. The higher structure are broken down into smaller, the smaller structure combined to give you the higher structure in the body. We have some major pathways involved in it. For example, glycolysis, gluconeogenesis, glycogen metabolism, fatty acid metabolism, citric acid cycle, amino acid metabolism, and oxidative phosphorylation. We have some compartments. Some of the enzyme or some of the processes, they took place only in the cytoplasm, and some of the reactions, they took place only in the mitochondria. However, some of them, they have some reaction in the mitochondria and some reaction in the cytoplasm. And why this compartmentalization is there? It is because of the presence of required enzyme. It is because of the presence of the required enzyme. So, for example, if you see here, glycolysis, pentose phosphate pathway, and fatty acid synthesis, the enzyme they are required for these pathways are present in cytoplasm. The enzyme required for citric acid cycle, beta oxidation, ketone bodies formation, they are present in the mitochondria. However, like gluconeogenesis and urea synthesis, they have some enzyme in cytoplasm and some enzyme in the mitochondria, so they have a dual action, they have dual site, they perform their function in two, or they are completed in two sites, cytoplasm as well as in the mitochondria. So this is the compartmentalization depending upon the presence of the enzymes. Now, if we see the core element, that is the glucose, and it's converted into glucose 6-phosphate, then this glucose 6-phosphate, we have different outcomes. It can give you the 6-ribose pentose phosphate pathway, it can enter into the pyruvate, or it can convert into glucose 6-phosphate and give you the glycogen. So here the reversible, here the reversible, and here it is irreversible and goes into the pentose phosphate pathway. Now, once the pyruvate is there, the pyruvate can go to lactate depending upon the requirement. If there is less oxygen, it will give you lactate. It can be converted into amino acids, alanine, or alanine can be converted into pyruvate. The process is called transamination. Or the pyruvate will convert into oxaloacetate and then goes to the glucose 6-phosphate and come back again. The pyruvate ultimate phase converted into acetyl-CoA and then converted into energy, carbon dioxide and water in the form in the TCA cycle. Acetyl-CoA converted into fatty acid, and then fatty acid is broken down again into acetyl-CoA. The acetyl-CoA converted into ketone bodies, 1,3-hydroxy, 3-methyl glutaryl CoA, HMG, hydroxy methyl glutaryl CoA, HMG CoA. And then we know that HMG CoA, either it will convert into ketone bodies or it can give you cholesterol. It can give you cholesterol. That's why you have a rate limiting enzyme here or irreversible enzyme here, that is HMG CoA reductase. And if you wanted to control the cholesterol, you would block that enzyme by HMG CoA reductase inhibitor. And then you can control the cholesterol. Okay, organs, they are involved. So brain, the most important one, least utilized, present with everyone, but least utilized. Muscles, liver, kidney and adipose tissue. We will see them quickly one by one. But in general, if we just see all these, brain is simple fuel consumer, white elephant. We call it in technical words white elephant. White elephant is something which is just consuming, is one of your friend who is always eating from you, never take you to burger fuel, always go with you and take it everything from you. So this is the brain. Liver and adipose tissue, they behave both sides. They as a fuel storage and tissue reservoir and reservoirs. Muscle, both generate, utilize, generate, utilize. And kidney is the faithful friend, a friend in need. when you need something and you want some friend to help you, that is the kidney. That is the kidney. So it helps you a significant source of energy under the starvation. So now you have clearly four kind of the people. Tamam? Number one, the one they are only users. Number two, the middle group, they store and give you something and take something from you. And the last one, which helps you in need, So here these are the organs: brain, lymphatic systems, adipose tissue, muscles, small intestine, portal vein, liver and pancreas. These organs are very much important in metabolic system. Adipocytes, their major function is triacylglycerol storage, free fatty acid and glycerol, and it is exported. And when it exports, when there is a fasting or you are in exercise. Liver, glycogen, again glucose and ketone bodies, VLDL, triacylglycerol. It can give everything. It can store glycogen, synthesize glycogen, break glycogen into glucose. When you need glucose, it gives you glucose. It collects the fatty acid and glycerol, synthesize triacylglycerol, and when you need it, it gives you. It synthesizes VLDL, LDL, HDL, and when you need it, it gives you. The only strange thing which is the liver is doing, that it's synthesizing ketone bodies, and it synthesizes ketone bodies when someone is fasting. And these ketone bodies are required for the brain, but he is such a kind person that he don't use this, because the enzyme which is required for the utilization of the ketone bodies, it is not present in the liver. Then skeletal muscle, we have glycogen and protein, and then we have lactate and alanine cycle, Cori cycle, intense exercise and fasting, it can help us. So brain, number one, 2% of the body, very small amount. Tamam? Glucose is the primary fuel. Brain lacks fuel store, so don't have any stores and require constant supply. And this is the most important thing. Utilizes 60% of the whole body glucose. 60% of the body glucose. That's why those they are brain worker, they are bench worker. Apparently the people see what they are doing nothing, just sitting in the office and then, but they are more tired in the evening as compared to someone who is hard working. That hard working is a muscular work, and this hard work is a brain work. And we know that 60% of the brain glucose body glucose is utilized by the brain. So that's why the people, they are very tired. The student, they are very tired in the evening. Consume 20% of the body oxygen, and fat can't store as a fuel, and we'll see why it is not. Some of the major reasons are there. One of the major reasons is that it cannot cross the blood-brain barrier. It needs a transporter for that. That's why it's difficult to use them. And under starvation, the brain is such an organ that it can use the ketone bodies as well. So this is the cycle. If there is a starvation, or if there is a normal diet, so glucose. If there is a starvation, then ketone bodies. And then they give ADP will be converted into ATP, and then this is the energy cycle. Now the question arises here, why brain use only glucose? Why the brain can't use fat? So three major reasons are there. Number one, we discussed that it cannot cross blood-brain barrier. Point number two, and they need a transporter. Point number two, if you remember your previous metabolic pathways, the catabolic pathways, the beta oxidation is the longest one, and it needs too much oxygen. So if brain utilizes fat and it needs too much oxygen, the higher chances are there that the neuron will become hypoxic. And you know that the brain is very sensitive to oxygen. So it will lead to hypoxia. Number two, why brain don't utilize the fatty acids or fat? Because if you just recall the beta oxidation, so many processes are involved there, and higher rate of free radical generation is there. Too much free radical is generated there. Superoxides are generated there. And when there are too much free radical and too much superoxide, the higher chances are there that the brain get damaged because of this oxidative stress. Tamam? So too much oxidative stress will damage the brain. And third, another important point, that brain needs quick energy. Brain needs quick energy. It cannot wait that energy will come and it will start function. Somebody hits you, you need to see quickly. By the time the energy comes, it sends message, and you see here the gentleman will be home, and we welcome our Honorable His Excellency the leader. Huh? So that's why it needs quick energy, and we know that quick energy is provided by the glucose, not by the fat. Fat gives you a high amount of the energy, but after a long process, and glucose gives you quick energy. So these are some of the some of the theories. Some of the theories, they say that it depends upon the constant supply of the brain, and this is the article. So you can go and see this article. Tamam? Clear? Now this is brain, and this is glucose, and glucose goes to the brain, and in some cases the liver provides ketone bodies, and ketone bodies is used by the brain. Muscles. Muscle account for 50%, brain account for 2%, not 20%, 2%. Oxygen consumption. And brain is how much? 50%. The mass, too much mass. If you have 60 kg, so maybe 30 kg will be the muscles. 30 kg will be the muscles. And muscle account for 50% of the total oxygen consumption. And during the vigorous exercise, the rate of consumption of oxygen increases to 90%. Tamam? And the respiratory rate increase 25 times, and ATP demand increase 100 times. The first 3 to 4 seconds of the energy is coming from phosphocreatine, and then afterwards the muscle metabolism starts, and then it gives you the energy. So, and the most important point is that the muscle store higher amount of the glycogen, because higher amount of the muscles, so higher amount of the glycogen. But the strange thing is with the muscle is that it do not supply glucose to the blood because of the deficiency of this enzyme, Okay, so here what happened normally, that pyruvate is converted. So when there is too much exercise and the people are deprived of oxygen, then what will happen? In the cycle goes to anaerobiosis, and there will be anaerobic glycolysis. And when there is an anaerobic glycolysis, so the pyruvate will convert into lactate. When the pyruvate is converted into lactate, so there can be two situations. Number one, lactic acid accumulation, and number two, what will happen, that this NADH will convert into NAD, and this NAD is required for the continuation of the glycolytic pathway. So it will go up and continue the glycolytic pathway. Point number one. And point number two, you see that there are two protons, they are free, they are set free. When two protons are set free, so in other words, the protons are also called hydrogen ions. And when the two hydrogen ions are set free, so the hydrogen ion concentration will be increased or decreased? When hydrogen ion concentration is increased, so the pH will increase or decrease? The pH will decrease. So when the pH is decreased, so there will be a localized acidosis. And this acidosis is a cause of pain, tiredness or fatigue. Pain, tiredness and fatigue. Clear? So this is NAD. So when pyruvate converted into lactate, this NAD is required for again NADH to continue the cycle. But in this cycle here, it releases two protons, and then it gives you pain, fatigue, and this one. Okay, one more thing, what happened here in the muscle. The accumulation of the lactic acid decrease the pH and reduce the muscle efficiency, and this releases to the muscle, and when it releases from the muscle, it goes to the liver, and when it goes to the liver, so in the liver it is again converted into pyruvate, and then from pyruvate to glucose, and then from glucose again to the muscle, and from the muscle again to the pyruvate, and from pyruvate again to the lactate, and then pyruvate again to the alanine, and this alanine will come out again to the liver. This cycle is called Core's cycle. This cycle is called Core's cycle, where the muscle make lactate, lactate come out, goes to the liver, in the liver again converted into glucose, again come back to the muscle, and the cycle is continuous. And this is muscle fatigue mechanism. We discussed this when 2 lactates are there, so it gives you 2 protons, this decreases the pH to 6.4, and then it leads to production of fatigue, and we have less energy, production of fatigue. So this is how the mechanism goes on. Okay, phosphocreatine, the level is about 10 to 30 millimole, 10 to 30 millimole of the phosphocreatine. And if you remember, we discussed this earlier as well, that phosphocreatine is behaving as car battery. So car is big one, the bigger car has a bigger engine, but that car has a small battery. So when you wanted to start your car, the initial thrust to start that car is coming from the battery. If you don't have working battery, you cannot start your car. Tamam? So that initial thrust of the energy is coming from the battery. But once the engine is start, so if you throw out the battery, what happened? Nothing, because now the engine function is there. So the initial function for the muscle is coming from the phosphocreatine. So this is phosphocreatine. It gives you the burst of heavy activity, and when it gives you ATP, and then this ATP will start with the muscle contraction and so on. But what happened to this phosphocreatine by itself? Once it releases the energy, creatine phosphate group, it is converted into this creatine, and then this creatine has 2 pathways, 2 outcomes. Either this is the phosphocreatine and this is creatine, and this is creatine kinase and ATP. This creatine has 2 outcomes. Either it will again rephosphorylate it, and again the cycle will be repeated, or you will remove water from this creatine, and then this creatine will be converted into creatinine. Very good. This creatinine will be converted into creatinine, and we know that creatinine is one of the good indicator for the assessment of kidney function. Good, very good. Muscles can't synthesize urea, so excrete large amount of the alanine to get rid of the ammonia, and we discussed this in glucose alanine cycle. Resting muscle use fatty acid and to beat the 85% of its energy. Heart, another muscular organ, highly rich in mitochondria, highly rich in mitochondria, because it needs quick energy, quick supply and continuous supply of the energy. So mitochondria occupy 40% of its cytoplasmic space. 40% of the cytoplasmic space. And heart excuse will be aerobic, has no glycogen store. Fatty acid are the primary source for the fuel, and can also use some glucose, pyruvate and lactate, and even the ketone bodies. Major function to provide fuel to the brain, muscles and other tissues, and it is the metabolic hub of the body, liver. Most compound absorbed from the diet must first go to the liver, and then from the liver to rest of the organ. 2/3 of the glucose in the blood removes by the liver. Glucose is converted to glucose 6-phosphate, glucokinase, hexokinase enzyme. Liver does not use glucose as a fuel, only as a source of carbon. Is skeleton for the synthetic materials, for the synthetic processes. And glucose 6-phosphate goes to the glycogen, and it is stored there. This is a very faithful organ because it gives you glucose. It has that enzyme glucose 6-phosphatase, and it is helpful for acetyl-CoA conversion of the lipids and fatty acid and cholesterol, help in the pentose phosphate pathways to generate NADPH, and a very good source for synthesizing of the lipoprotein. It synthesizes ketone bodies, but it cannot use ketone bodies. Here are the ketone bodies: HMG-CoA, acetoacetate, hydroxybutyryl-CoA, but they cannot use these ketone bodies because this enzyme thiophorase is deficient here, and this is present in the muscles. So the ketone bodies, they goes to the muscle, utilized there, or it goes to the brain and it is utilized in the brain. So liver absorbs majority of the amino acids, and these amino acids are primarily used for the protein formation. Extra amino acids present in the liver obtained from glucose alanine cycle, they are oxidized and catabolized, and carbon skeletal for the amino acid directed towards the gluconeogenesis for the fuel. So here this is glucose, liver glycogen, blood glucose, pentose phosphate pathway or nucleoside synthesis, pyruvate acetyl-CoA, acetyl-CoA to the cholesterol and fatty acids. Amino acids, liver proteins, then proteins of the tissue and muscles, broken down, ammonia is released, pyruvate converted to acetyl-CoA, enter into the citric acid cycle, and this ammonia will enter into the liver and then will give you the urea. Fatty acids goes to the liver, utilize there, make LDL, HDL and VLDLs, goes to the plasma lipoprotein or free fatty acid in the blood, or enter into the cell, oxidize by the process of beta oxidation, gives you acetyl-CoA. This acetyl-CoA enter into the TCA cycle or gives you cholesterol bile synthesis, and so many hormones, steroid hormone here. Adipose tissue primary function is to store and release the fatty acid when it is required, and it stores the fat at the form of TGs, and it can store TGs in an enormous situation. And we discussed earlier the function of adipose tissue as an endocrine gland, because it releases adipokines. Two type of there, one is leptin and another one is adiponectin. So enormous fat stored triglyceride, it's up to you. Fat is important into adipocyte from the chylomicron and VLDL, and once in the cell they are esterified into glycerol backbone and glucagon, epinephrine, they stimulate the response of this. So here is the glucose coming from the blood, VLDL, fatty acid, and in the adipose tissue it makes TGs, hormone sensitive lipase, break into glycerol and fatty acid, and then again into the blood. So this is the cycle. This is the area where you can store too much. So there will be increase in the size and increase in the number as well. In juvenile type or early type or the young age obesity, if you remember we discussed earlier that is the increase in the number of the adipocytes. That's why young age obesity is very difficult to be reduced. However, in the old age obesity it is easily to be reversed back, because in the old age only the size is increased, in the young age the number is also increased. Then kidneys, faithful friend. Production of the urine, secretion of waste product, blood plasma is filtered, water and glucose are reabsorbed, and during starvation it is very much important for the production of glucose, half of the cycle there in the glucose, so it is very good in the gluconeogenesis. Clear?
But this is after the prolonged starvation.
Tamam? Even gluconeogenesis is a continuous process, not only dependent upon the prolonged starvation. In between the meals we have a process of gluconeogenesis, because the gluconeogenesis is not only one pathway to provide the glucose, but rather it is also utilized to remove the waste product as well. Like for example lactate, alanine, all some other compounds, keto acid, they are converted into amino acid and then they are utilized. So the pathways are very well connected. Tamam? Clear, guys?
The other half roughly the liver, right?
Sorry?
The other half which gluconeogenesis.
Yeah, cytoplasm in liver. Thank you very much.